Brain, what is root cause analysis? A philosophical and conceptual view. At its core, root cause analysis, RCA, is more than a tool or technique. It's a way of thinking, a philosophy of problem solving that seeks not just to fix issues, but to deeply understand them. In life and in systems, what we observe as failure is often only the symptom, the visible tip of an iceberg. RCA challenges us to look beyond surface events and to ask why, again and again, peeling back layers of causation until we reach the true source, the origin point that gave rise to the problem. Philosophically, RCA is grounded in the idea that everything happens for a reason, and that systems behave the way they are designed, or allowed, to behave. This means failures aren't accidents. They're often the inevitable result of hidden weaknesses, overlooked variables, or flawed assumptions. From a conceptual standpoint, RCA is a journey from effect to cause, not just backwards in time, but inward into the system's design, process, and human decisions. A shift from blame to understanding, where the focus is not who caused it, but what allowed it to happen. A tool of organizational wisdom, because identifying and correcting root causes leads to learning, evolution, and improvement. Just as a tree's fruit reflects the health of its roots, a system's outcomes reflect the integrity of its foundations. RCA is the method by which we trace the branches of failure back to the root so we can strengthen the whole. Systematically identify the underlying causes of problems or incidents instead of treating symptoms. RCA digs deep to uncover the real source of issues. Move beyond temporary fixes by finding permanent. Preventive solutions helps avoid recurring problems by addressing what truly went wrong. Use existing data to develop a logical, evidence-based problem-solving strategy. Leverages internal records, logs, and experience to inform better decisions. Establish a repeatable, step-by-step process where each stage validates the previous one. Builds reliability into the analysis process, making it consistent and verifiable. Understand system barriers and breakdowns to reduce the likelihood of recurrence. Looks at where the process failed, be it in communication, design, training, or oversight. Shift from reactive firefighting to proactive and effective management. Enables organizations to be strategic and forward-thinking instead of constantly reacting. Into the analysis process, making it consistent and verifiable. Understand system barriers and breakdowns to reduce the likelihood of recurrence. Looks at where the process failed, be it in communication, design, training, or oversight. Shift from reactive firefighting to proactive and effective management. Enables organizations to be strategic and forward-thinking instead of constantly reacting. Root cause analysis, RCA, is a powerful problem-solving tool with wide-ranging applications across various industries. In manufacturing and production, RCA helps identify the underlying causes of equipment failures, quality issues, and downtime, leading to improved reliability and efficiency. In process industries such as pharmaceuticals, oil and gas, and chemicals, RCA is used to investigate safety incidents, process deviations, and compliance issues, often uncovering procedural flaws or human errors. In business and marketing, RCA assists in understanding issues like declining sales or poor campaign performance by pinpointing root causes, such as ineffective messaging or targeting. Financial institutions use RCA to examine transaction failures, fraud, or system outages, allowing them to improve operational resilience and customer trust. In IT and software development, RCA is key in diagnosing recurring bugs, system crashes, and data loss, revealing underlying technical or procedural weaknesses. Healthcare organizations apply RCA to improve patient safety by analyzing incidents, such as medication errors or procedural lapses. In the education sector, RCA helps uncover reasons behind poor student performance or ineffective teaching methods. Overall, RCA offers a structured, logical, and data-driven approach that helps organizations across sectors shift from reactive problem-solving to proactive and preventive strategies. Setting clear policies at the organizational level for when to conduct a formal root cause analysis, RCA, is essential for effective and consistent problem-solving. These policies should define specific triggers such as the severity of the incident, the level of risk involved, recurrence of the issue, safety implications, and financial impact. For example, A formal RCA may be mandated for any incident resulting in significant production loss, safety hazards, regulatory noncompliance, or costs exceeding a defined threshold. By establishing such criteria, organizations can ensure resources are allocated efficiently, focusing formal investigations on high-impact problems while allowing simpler issues to be addressed through quicker corrective actions. This approach fosters a culture of continuous improvement and risk-informed decision-making. A major classification of problems that often warrants RCFA are those events associated with the failure of critical production equipment, machinery, or systems. Generally, any incident that results in partial or complete failure of a machine or process system warrants a RCFA. This type of incident can have a severe negative impact on plant performance. Therefore, it often justifies the effort required to fully evaluate the event and to determine its root cause. Events that result in physical damage to plant equipment or systems are the easiest to classify. Visual inspection of the failed machine or system component usually provides clear evidence of its failure mode. While this inspection usually will not resolve the reason for failure, the visible symptoms or results will be evident. The events that also meet other criteria, e.g., safety, regulatory, or financial impact, should be investigated automatically to determine the actual or potential impact on plant performance, including equipment reliability, operating performance. Deviations in operating performance may occur without the physical failure of critical production equipment or systems. Chronic deviations may justify the use of RCFA as a means of resolving the recurring problem. Generally, chronic product quality and capacity problems require a full RCFA. However, care must be exercised to ensure that these problems are recurring and have a significant impact on plant performance before using this problem-solving technique. Product quality. Deviations in first time through product quality are prime candidates for RCFA, which can be used to resolve most quality-related problems. However, the analysis should not be used for all quality problems. Non-recurring deviations, or those that have no significant impact on capacity or costs, are not cost-effective applications. Capacity restrictions. Many of the problems or events that occur affect a plant's ability to consistently meet expected production or capacity rates. These problems may be suitable for RCFA, but further evaluation is recommended before beginning an analysis. After the initial investigation, if the event can be fully qualified and a cost-effective solution not found, then a full analysis should be considered. Note that an analysis normally is not performed on random, non-recurring events or equipment failures. Economic performance. Deviations in economic performance, such as high production or maintenance costs, often warrant the use of RCFA. The decision tree and specific steps required to resolve these problems vary depending on the type of problem and its forcing functions or causes. Safety. Any event that has a potential for causing personal injury should be investigated immediately. While events in this classification may not warrant a full RCFA, they must be resolved as quickly as possible. Isolating the root cause of injury-causing accidents or events generally is more difficult than for equipment failures and requires a different problem-solving approach. The primary reason for this increased difficulty is that the cause often is subjective. Regulatory compliance. Any regulatory compliance event can have a potential impact on the safety of workers, the environment, as well as the continued operation of the plant. Therefore, any event that results in a violation of environmental permits or other regulatory compliance guidelines, e.g., Occupational Safety and Health Administration, Environmental Protection Agency, and state regulations, should be investigated and resolved as quickly as possible. Since all releases and violations must be reported and they have a potential for curtailed production or fines, or both, this type of problem must receive a high priority. Interviews. All personnel directly involved with the incident, be sure to review data gathering for root cause analysis. Interviews. All personnel directly involved with the incident, be sure to review any supervisors and managers of those involved in the incident, including personnel not directly involved in the incident, but who have similar background applicable technical experts, training personnel, and equipment vendors, written witness statements ground and experienced suppliers, or manufacturers. It is important for the interviewer to clearly inform the reasons for the evaluation to the interviewee at the beginning of the interview process. What happened? Where did it happen? When did it happen? What changed?
Who was involved?
Why did it happen? What is the impact? Will it happen again? How can recurrence be prevented? Collecting physical evidence. Currently approved standard operating, SOP, and maintenance, SMP, pro-company policies that govern activities performed during the event. Operating and process data, e.g., strip charts, computer output, and data recorder information. Appropriate maintenance records for the machinery or area involved in the event. Copies of logbooks, work packages, work orders, work permits, and maintenance records, equipment test results, quality control reports, oil and lubrication analysis results, vibration signatures, and other records. Diagrams, schematics, drawings, vendor manuals, and technical specifications, including pertinent design data for the system or area involved in the incident. Training records, copies of training courses, and other information that shows skill levels of personnel involved in the event. Photographs, videotape, or diagrams of the incident scene. Broken hardware, e.g., ruptured gaskets, burned leads, blown fuses, failed parts for the machine or area where the event occurred. Bearings. Analyze sequence of events. Performing a sequence of events analysis and graphically plotting the actions leading up to and following an event, accident, or failure helps visualize what happened. It is important to use such a diagram from the start of an investigation. This not only helps with organizing the information but also in identifying missing or conflicting data, showing the relationship between events and the incident, and highlighting potential causes of the incident. Design review. It is essential to clearly understand the design parameters and specifications of the systems associated with an event or equipment failure. Unless the investigator understands precisely what the machine or production system was designed to do and its inherent limitations, it is impossible to isolate the root cause of a problem or event. The data obtained from a design review provide a baseline or a reference, which is needed to fully investigate and resolve plant problems. The objective of the design review is to establish the specific operating characteristics of the machine or production system involved in the incident. The evaluation should clearly define the specific function or functions that each machine and system was designed to perform. In addition, the review should establish the acceptable operating envelope or range that the machine or system can tolerate without a measurable deviation from design performance. Equipment nameplate data. Most of the machinery, equipment, and systems used in process plants have a permanently affixed nameplate that defines their operating envelope. For example, a centrifugal pump's nameplate typically includes its flow rate, total discharge pressure, specific gravity, impeller diameter, and other data that define its design operating characteristics. These data can be used to determine if the equipment is suitable for the application and if it is operating within its design envelope involved in the incident. The evaluation should clearly define the specific function or functions that each machine and system was designed to perform. In addition, the review should establish the acceptable operating envelope or range that the machine or system can tolerate without a measurable deviation from design performance. Equipment nameplate data. Most of the machinery, equipment, and systems used in process plants have a permanently affixed nameplate that defines their operating envelope. For example, a centrifugal pump's nameplate typically includes its flow rate, total discharge pressure, specific gravity, impeller diameter, and other data that define its design operating characteristics. These data can be used to determine if the equipment is suitable for the application and if it is operating within its design envelope. Procurement specifications. Procurement specifications normally are prepared for all capital equipment as part of the purchasing process. These documents define the specific characteristics and operating envelope requested by the plant engineering group. The specifications provide information useful for evaluating the equipment or system during an investigation. When procurement specifications are unavailable, purchasing records should describe the equipment and provide the system envelope. Although such data may be limited to a specific type or model of machine, it generally is useful information. Vendor specifications. For most equipment procured as a part of capital projects, a detailed set of vendor specifications should be available. Generally, these specifications were included in the vendor's proposal and CONKED as part of the deliverables for the project. Normally, these records are on file in two different departments, purchasing and plant engineering. As part of the design review, the vendor and procurement specifications should be carefully compared. Many of the chronic problems that plague plants are a direct result of vendor deviations from procurement specifications. Carefully comparing these two documents may uncover the root cause of chronic problems. Operating and maintenance manuals. O&M manuals are one of the best sources of information. In most cases, these documents provide specific recommendations for proper operation and maintenance of the machine, equipment, or system. In addition, most of these manuals provide specific troubleshooting guides that point out many of the common problems that may occur. Incoming product specifications. Machine and system functions depend on the incoming product to be handled. Therefore, the design review must establish the incoming product boundary conditions used in the design process. In most cases, these boundaries include temperature range, density or specific gravity, volume, pressure, and other measurable parameters. These boundaries determine the amount of work the machine or system must provide. In some cases, the boundary conditions are absolute. In others, there is an acceptable range for each of the variables. The review should clearly define the allowable boundaries used for the system's design. Output. Product specifications. Assuming the incoming product boundary conditions are met, the investigation should determine what output the system was designed to deliver. As with the incoming product, the output from the machine or system can be bound by specific, measurable parameters. Flow, pressure, density, and temperature are the common measures of output product. However, depending on the process, there may be others. Work to be performed. This part of the design review should determine the measurable work to be performed by the machine or system. Efficiency, power usage, product loss, and similar parameters are used to define this part of the review. The actual parameters will vary depending on the machine or system. In most cases, the original design specifications will provide the proper parameters for the system under investigation. Acceptable operating envelope. The final part of the design review is to define the acceptable operating envelope of the machine or system. Each machine or system is designed to operate within a specific range, or operating envelope. This envelope includes the maximum variation in incoming product, startup ramp rates and shutdown speeds, ambient environment, and a variety of other parameters. Process parameters. Evaluating variations in process parameters, such as pressures, flow rate, and temperature, is an effective means of confirming their impact on the production system. In some cases, the Level 1 computer monitoring systems used to operate the process system provide much of the data needed. Measurement devices. Most machines and systems include measurement devices that provide a clear indication of the operating condition. A visual inspection of these devices confirms many of the failure modes that cause process deviations and catastrophic failures. Failed machine components. Visual inspection of failed machine components can be an effective diagnostic tool. For example, visual inspection of a failed bearing can determine the load zone, wear pattern, and in many cases the probable cause of the failure. The same is true of gears, V-belts, and a variety of other common machine components. Causes of failure or problems in an industrial or organizational setup can generally be categorized into three types by nature: physical, human, and organizational. Each plays a distinct role but is often interconnected, creating a complex web of root causes. Understanding their individual roles and relationships helps in diagnosing issues effectively. 1. Physical causes. These are tangible, measurable, and technical in nature, such as equipment failure, material fatigue, corrosion, overheating, or poor design. Physical causes are usually the most visible symptoms in a failure scenario, but they are rarely the true root cause on their own. For instance, a broken shaft might be due to repeated overloading, but why it was overloaded leads us deeper. 2. Human causes. These refer to errors or decisions made by individuals, mistakes, lapses, or violations. These can include improper operation, poor maintenance, inadequate training, or failure to follow procedures. Often, human causes are responses to the environment or system in which people work, and they may lead to physical consequences. However, simply blaming individuals ignores the deeper systemic issues that influence their behavior. 3. Organizational causes. These are systemic and cultural in nature and often form the foundation for recurring problems. They include policy gaps, unclear responsibilities, poor communication, weak leadership, inadequate resource allocation, and ineffective training programs. Organizational causes create the environment in which human and physical errors become more likely. For example, an operator making an error might do so because of excessive workload or unclear SOPs, which are organizational issues. Interrelationship. These causes are not isolated. Organizational weaknesses often influence human behavior, which in turn may lead to physical failures. Conversely, recurring physical issues may reveal deeper training or policy deficiencies. In effective root cause analysis, RCA, understanding how these 3 layers interact is crucial. Solving just the physical problem without addressing human or organizational contributors will likely result in recurrence. For sustainable improvement, organizations must move beyond the visible, physical, and immediate human causes to address the underlying systemic, organizational factors. This layered approach ensures deeper learning and more robust solutions. In the context of root cause analysis, RCA, causal factors and barrier analysis are 2 core tools used to understand how and why an unwanted event occurred. Together, they help trace the chain of events and identify opportunities where the failure could have been prevented. Causal factors. Causal factors are the events, conditions, or actions, or lack thereof, that contributed to the occurrence of the unwanted outcome. These are not always root causes, but they are key contributors in the failure path. Identifying them allows us to construct a cause-effect chain that ultimately leads to the root cause. For example, if a pump failed due to overheating, causal factors might include blocked cooling vents, delayed maintenance, misread temperature gauge, or lack of operator attention. Causal factors help answer the question, what happened and what allowed it to happen? They are developed by gathering evidence, data, logs, interviews, etc., mapping the timeline and sequence of events, using tools like the 5 whys, fishbone diagrams, or cause trees. Barrier analysis. Barrier analysis focuses on identifying controls or safeguards that should have prevented or mitigated the event, and why they failed or were absent. Barriers can be physical, administrative, or procedural, and are typically put in place to stop a hazard from reaching a target, like a person, equipment, or the environment. Barriers answer the question, what should have stopped this from happening, and why didn't it? Types of barriers might include physical, guards, alarms, interlocks. Human, training, awareness, standard operating procedures. Organizational, policies, supervision, audits. By analyzing the failure or absence of these barriers, RCA uncovers systemic weaknesses and helps in strengthening defenses for the future. Integration in RCA process. When combined, causal factor analysis identifies what led to the failure, while barrier analysis assesses what allowed those causal factors to succeed. This integrated view provides a comprehensive understanding of how failures unfold and where interventions are most effective. Ultimately, the goal is not just to correct the immediate problem but to rebuild resilience into the system, eliminating root causes, reinforcing barriers, and preventing recurrence. Barrier analysis, particularly when combined with a cheese hole theory, often associated with Swiss cheese model, is a safety and risk management approach that focuses on identifying and analyzing safety barriers that could prevent accidents or failures. Barrier analysis. Barrier analysis is a method used to identify the various layers of defense that exist within a system to prevent failures or accidents. These barriers can include physical, procedural, or human factors, and their goal is to provide multiple layers of protection against potential hazards. The process involves identifying hazards, identifying potential risks or hazards that could cause harm, damage, or failures, analyzing barriers, Examining the existing safety barriers, e.g., alarms, safety protocols, training, procedures, equipment that are designed to prevent the hazards. Evaluating barrier effectiveness, assessing how well each barrier works, and identifying potential weaknesses or holes in the safety system where the risk of failure may increase. Improvement actions, identifying and implementing improvements to address gaps in the barriers. Swiss cheese model. The Swiss cheese model, proposed by James Reason in 1990, is a metaphorical framework used to understand how accidents or failures occur in complex systems. In this model, each layer of cheese represents a safety barrier. The holes in the cheese represent weaknesses or flaws in those barriers, e.g., human error, technical failures, design flaws. Accidents happen when the holes in each layer align, allowing a hazard to pass through all the barriers, leading to a failure or accident. The concept is that multiple layers of defense, even if imperfect, reduce the likelihood of accidents. However, if several weaknesses align, like holes in multiple slices of Swiss cheese, a system failure can occur. How barrier analysis and the Swiss cheese model work together. Barrier analysis can be enhanced by the Swiss cheese model because it allows you to visualize how safety barriers can fail in conjunction with each other. The process works like this. Barrier identification. Each layer of defense, such as technical systems, safety protocols, or human intervention, is seen as a slice of Swiss cheese. Weakness detection. Holes in each layer, indicating failure points, are identified through analysis and inspection. Risk management. By recognizing where the holes align, organizations can implement measures to plug these gaps, improving the overall safety system and reducing the risk of an accident. In this way, barrier analysis with the cheese hole theory helps to ensure that systems are designed with multiple layers of defense, reducing the likelihood that all barriers will fail at once and ensuring more resilient systems. Benefit of systematic RCA approach. Continuous improvement culture. Regular use of quality and RCA tools fosters a culture of continuous improvement within the organization. It establishes a mindset where teams are encouraged to identify and address issues systematically rather than merely reacting to problems. Preventive approach. Quality tools help identify potential issues before they escalate, allowing organizations to take a preventive approach. Regularly conducting root cause analyses enables proactive problem solving, reducing the likelihood of recurring problems. Cost savings. Addressing the root causes of issues prevents their recurrence, leading to cost savings associated with problem resolution, downtime, rework, and customer complaints. Investing time and resources in regular analysis can have a significant long-term financial impact. Enhanced productivity. Identifying and eliminating root causes of inefficiencies or defects improves overall productivity. Teams can focus on value-adding activities rather than dealing with recurring issues. Customer satisfaction. Consistent use of quality tools ensures that products or services meet or exceed customer expectations. Satisfied customers are more likely to remain loyal and contribute positively to the organization's reputation. Risk mitigation. Regular analysis helps in identifying and mitigating risks before they lead to major issues. Proactively managing risks through RCA tools reduces the likelihood of unexpected disruptions. Data-driven decision-making. Quality tools rely on data and evidence to identify problems and their root causes. Regular use of these tools promotes data-driven decision-making, ensuring that actions are based on facts rather than assumptions. Employee engagement. Involving employees in the RCA process fosters a sense of ownership and engagement. Employees feel empowered to contribute to problem-solving and are more likely to be invested in the success of the organization. Compliance and standards. Regular use of quality tools helps organizations adhere to industry standards and compliance requirements. It ensures that processes are aligned with best practices and regulatory guidelines. Learning and skill development. Regular use of RCA tools provides opportunities for employees to enhance their problem-solving and analytical skills. It contributes to a learning culture within the organization. Incident documentation. Capture and document details of incidents or problems, including descriptions, timelines, and relevant data. Cause and effect analysis. Tools for creating cause and effect diagrams, Ishikawa or fishbone diagrams, to visually represent the relationships between various factors contributing to an issue. Data analysis. Statistical tools and data visualization capabilities for analyzing quantitative data related to incidents or problems. Collaboration and communication. Collaboration features to facilitate communication among team members involved in the RCA process, enabling real-time collaboration and information sharing. Root cause identification. Support for systematic identification and analysis of root causes, often through techniques like the 5 whys or other problem-solving methodologies. Action planning. Tools for developing and tracking corrective actions or preventive measures to address identified root causes. Workflow management. Workflow features to manage the entire RCA process, from initial incident reporting to the implementation and tracking of corrective actions. Knowledge creation. Reusability of learnings, a step toward use of artificial intelligence. Feature of documented/software-supported RCA. Risk assessment. Integration of risk assessment tools to evaluate the potential impact and likelihood of recurrence of identified issues. Document management. Document repository for storing relevant documents, reports, and evidence related to incidents and the RCA process. Audit trail. Maintain a comprehensive audit trail to track changes, actions taken, and decisions made throughout the RCA process, ensuring transparency and accountability. Reporting and dashboards. Generate comprehensive reports and dashboards that provide insights into the RCA process, including trends, common issues, and the effectiveness of implemented solutions. Integration with other systems. Integration capabilities with other business systems, such as incident management, quality management, or risk management systems. User permissions and security. Ensure data security and privacy with features for user permissions, access controls, and secure data storage. Concept of tools in mechanical and quality contexts. In the mechanical world, tools are essential instruments that help carry out specific tasks. Just as a hammer is used to drive nails, each tool in quality management serves a specific purpose in addressing different aspects of quality. Quality tools, much like mechanical tools, help identify, analyze, and solve problems to ensure smooth operations and continuous improvement. These tools are grouped into families based on their application and scale. Quality tools and their families. Quality tools are categorized into families based on their function, and each tool helps tackle issues at different stages of problem-solving or process improvement. Here, we'll look at the basic 7 quality tools, which are the core set of tools frequently used in quality management to analyze and improve processes. 1. Cause and effect diagram, fishbone or Ishikawa diagram. Purpose. Used to identify the potential causes of a specific problem. Example, if a machine is producing defective parts, the fishbone diagram could explore possible causes such as machine failure, material quality, or human error, categorizing them into categories like people, process, equipment, materials, environment, and management. 2. Check sheet. Purpose. A simple tool to collect and organize data for analysis. It helps track occurrences of specific issues over time. Example, in a factory, a check sheet might be used to record the number of defects observed in a batch of products, helping to identify trends and patterns. 3. Control chart. Purpose. A graphical tool used to monitor how a process changes over time and whether it stays within acceptable limits. Example, a control chart can be used to track the temperature in an industrial oven during production. If the temperature falls outside the control limits, it indicates a potential problem that needs attention. 4. Histogram. Purpose. A type of bar chart that represents the frequency distribution of data, helping to identify patterns and variations. Example, in a manufacturing process, a histogram might show the distribution of the diameter of parts produced, helping to identify if the parts are consistently within specification or if there's variability that needs to be controlled. 5. Pareto chart. Purpose. A bar chart that uses the 80-20 rule to show which factors contribute the most to a problem, helping to prioritize solutions. Example, if customer complaints are being tracked, A Pareto chart might show that 80% of complaints are due to just a few common issues, such as shipping errors or defective products. 6. Scatter diagram. Purpose. A graph that shows the relationship between two variables. It helps identify potential correlations. Example, in an engineering context, a scatter diagram could be used to show the relationship between machine temperature and defect rates, helping to determine if higher temperatures are correlated with more defects. 7. Flowchart. Purpose. A diagram that represents the steps in a process, helping to visualize and understand workflows. Example, a flowchart could be used to map out the steps in an assembly line process, helping to identify potential inefficiencies or bottlenecks in the system. Basic 7 quality tools. Just as mechanical tools, like a hammer or a wrench, serve different purposes in physical tasks, these quality tools are designed to address different aspects of quality improvement, from problem identification to process monitoring, and help build more efficient, reliable systems in various industries.
Quality Tool Matrix. 1. Project Planning and Implementation Tool. Purpose. Used when managing and executing projects. Key use. These tools help in defining objectives, timelines, responsibilities, and milestones. Examples. Gantt chart. Visual project timeline and task management. PERT chart. Program evaluation and review technique shows task dependencies and critical path. Project charter. Document outlining the scope, objectives, and stakeholders of a project. 2. Idea creation tools. Purpose. Used to generate new ideas or organize brainstorming outputs. Key use. Encourages creativity and idea flow when tackling a new or undefined problem. Examples. Brainstorming, group idea generation. Mind mapping, visual representation of connected ideas. Affinity diagram, groups related ideas into categories for better clarity. 3. Process analysis tools. Purpose. Helps in understanding and visualizing how a process works. Key use. Identify inefficiencies, bottlenecks, or improvement areas. Examples. Flowchart. Maps out the step-by-step process visually. SIPIC diagram. Suppliers, inputs, process, outputs, customers gives a high-level view of a process. Value stream mapping. Identifies value-adding and non-value-adding steps. 4. Data collection and analysis tools. Purpose. Gather and analyze data to understand a problem. Key use. Data-driven decision-making and problem diagnosis. Examples. Check sheet. Tracks frequency of events. Histogram. Shows the distribution of data. Control chart. Tracks variations over time to monitor process stability. 5. Cause analysis tools. Purpose. Discover the root causes of problems. Key use. Go beyond symptoms to prevent recurrence of issues. Examples. Fishbone diagram. Ishikawa categorizes potential causes. 5 whys. Repeatedly asking why to drill down to the root cause. Fault tree analysis. FTA visualizes failure pathways. 6. Evaluation and decision-making tools. Purpose. Evaluate options. Select the best one or assess performance. Key use. Useful when choosing among alternatives or measuring results. Examples. Decision matrix. Pew matrix compares multiple options against weighted criteria. Cost-benefit analysis. Assesses the financial impact of decisions. Benchmarking. Compares performance to best practices or standards. Summary table. Tool family main purpose key tool examples project planning and implementation manage and control projects Gantt chart. PERT chart idea creation generate and organize ideas brainstorming. Mind map process analysis understand how a process works flowchart. SIPIC. VSM data collection and analysis collect and interpret data check sheet. Histogram. Control chart cause analysis identify root causes of problems fishbone. 5 whys. FTA evaluation and decision making choose the best solution or evaluate. Outcomes decision matrix. CBA. Benchmarking. Quality core tools. APQP. Advanced product quality planning. APQP and control plans reduces the complexity of product quality planning. PPAP. Production part approval process. PPAP is the industry standard that ensures engineering design and product specification requirements are met. FMEA, failure mode and effects analysis. FMEA is a tool used to identify and address failure modes in products and processes. SPC, Statistical Process Control, SPC, describes several basic and advanced statistical methods to ensure your process improvements are more effective. MSA, Measurement System Analysis. MSA, measurement data monitors nearly every process. As data quality improves, decision quality improves. Effects Analysis, FMEA, is a tool used to identify and address failure modes in products and processes. SPC, Statistical Process Control, SPC, describes several basic and advanced statistical methods to ensure your process improvements are more effective. MSA, Measurement System Analysis. MSA, measurement data monitors nearly every process. As data quality improves, decision quality improves. Mega Quality Tools. Quality Function Deployment, QFD. It is structural process of planning the design of a new product or service or for redesign the existing one. ISO 9000. These are set of international standards for quality. Organizations are audited and certified against the requirement of standards. Benchmarking. Benchmarking is a structural process for comparing your organization's work practices to the best similar practices you can identify in other organizations and then incorporate these best ideas into your process. Six Sigma is an approach used to achieve breakthrough improvements. Unlike other approaches, Six Sigma specified exactly how managers should set up and lead the efforts. Mega Quality Tools. Quality Function Deployment, QFD. It is structural process of planning the design of a new product or service or for redesign the existing one. ISO 9000. These are set of international standards for quality. Organizations are audited and certified against the requirement of standards. Benchmarking. Benchmarking is a structural process for comparing your organization's work practices to the best similar practices you can identify in other organizations and then incorporate these best ideas into your process. Six Sigma is an approach used to achieve breakthrough improvements. Unlike other approaches, Six Sigma specified exactly how managers should set up and lead the efforts. Lean manufacturing. It refers to a system of methods that emphasize identifying and eliminating all non-value-adding activities waste for manufacturing and manufacturing support system. Malcolm Baldrige National Quality Award. MBNQA criteria provide a guide for developing management system that can achieve high level of quality, productivity, customer satisfaction, and marketing success. This is the list of quality tools that can serve the variety of situation. Pause the videos and look out for the tools you may require for your pressing problems.